The position vector that is indicating the positions of M1 and M2 is indicated by R1, that is vector R1 and vector R2. It is not exactly at the middle, but there appears to be a point where I can balance the entire mass of this particular object. The entire particle is going to move like this, and this R is nothing but indicating the position vector of center of mass. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with system of particles and rotational motion. So we saw like analogous terms from linear motion to rotational motion. Let's continue on to that and see what else is waiting for us. So we do know that any moving object will possess a kinetic energy. That is, if any object that is having a mass of m is moving with a velocity of v, it is going to possess the kinetic energy that is expressed by half mv square. That is a truth. Now, what if this particular object is going in a circular pattern, or it is spinning, or it is rotating about an axis, or rotating about a common center position? Then what will happen to that particular object? That is this question. Or what will happen to the kinetic energy of the particular object that is rotating about a fixed point? Obviously, we cannot use mv square because again, v is only expressed in linear terms, right? If any object is going around or it is following an angular pattern, we cannot use linear velocity v because the direction will be constantly changing at every point when it is going in a circular pattern. So we cannot use that particular equation. Again, if I apply that particular logic which we apply to the equation for torque and moment of inertia and all that, we know that Ke is equal to half mv square. So obviously its rotational analog will be, it's easy, right? Ke, let's say this is rotational kinetic energy. So rotational kinetic energy will be equal to half, no need to convert it because half is a constant. In rotational motion also half will be half. So this will be half. And again, mass will be converted into analogous of mass in rotational motion is moment of inertia. So we can say that it will become I. And analogous of v, velocity will become angular velocity. So it will be written as I omega square. So this is the general equation for kinetic energy in rotational motion. But again, this is not enough. Applying logic and guessing the equations is not actually a scientific proof. So we have to derive what the kinetic energy of a particle or a system of particle rotating around a particular axis will be equal to. So let's get on to that particular derivation. So expression for a rotating body which is rotating about an axis, that is what we are going to do here. It is very simple. Again, all you have to do is that assume there is a particular body. In this particular case, let it be a disk. So there is a disk about a certain axis which is going to be rotating. So if I say that this particular disk is rotating about this particular axis, then I can say that okay, every particle on this particular disk, every particle, let's say M1, M2, M3, etc. Here, every particle is rotating, right? The only thing differing is the radius. Other than that, every particle is rotating about this particular fixed axis at an angular speed of omega or angular velocity of omega. So we do know that there is a disk and it is rotating about a particular axis at the speed or at the velocity of omega. Now, in that particular case, I am taking a random particle that is mi. Some random particle on this disk I am selecting at random like this. Okay, let it be mi. Generally, let it be mi. And it is at ri distance from the center or from the particular axis. It is located at ri distance. Now, when this particular mass particle is rotating about an axis, we can say that okay, it has angular velocity. Its linear velocity will always be tangential to the rotation, right? If I take the linear velocity of that particle at any point in time, we can say that okay, this will be the direction of linear velocity. That is why we take angular velocity. So mass particle, let's say m1 or mi, which is at Ri distance from the axis is now rotating about that particular axis going at a speed of omega, right? So how can I write the kinetic energy of that particular particle? So if I write kinetic energy in linear sense, it is equal to half mv square, but in rotational sense, okay, I am saying that in rotational sense, a mass particle, in rotational sense, I have to find an expression for the mass particle, right? So first I'll start from the linear equation. So the linear equation states that, okay, Ke is equal to half mv square, right? So since there are n number of particles and n number of radiuses or n number of velocities recorded here, I'm going to take any random position just like this. So for example, I'm taking for mass mi and radius ri, right? So I'm saying that, okay, there is some random particle which is having a mass of mi, which is moving at a particular velocity of vi. That is, if I take this particular mass, if I take the linear velocity of that particular point mass, then I can say that, okay, it will be in this particular direction and it will be vi, right? So I can say that, okay, then I can say that kinetic energy will be expressed as half mi vi square at that particular instant in time for that one particle. Okay, now the only problem is that this is a linear equation which I cannot apply to rotational motion. So how can I convert this into rotational sense? It's very simple. The only thing I have to convert actually is this v, because again v is velocity. When velocity is written in a rotational sense, we already know that what is the rotational analog of linear velocity. What is it? It is equal to omega r, right? Remember the derivation? We saw that theta was equal to displacement times radius, right? Or theta by r was equal to s. And then again, I divide both side by t, then I can get angular displacement omega is equal to vr. We did this in the last class. So it is very easy. So we can have an expression for velocity which is equal to omega times r. Now, if I substitute this particular equation into this, what will I get? If I substitute this particular equation into the above equation, okay, I'll write it neatly. So the first thing we do know is that the kinetic energy is given by the expression which is half mv square. But we know that we are checking for a random particle, let's say the ith particle. So it is going to have a mass of mi and a velocity of vi. But again, we know that velocity is actually equal to r times omega, right? So we can say that for the ith particle, we can say that vi will be equal to ri into omega I, or just ri omega, both are fine. So then we can say that, substituting, this is equation number 1, this is equation number 2. So substituting equation number 2 in equation 1, I can say that 2 in 1, I can say that Ke will be equal to, that is kinetic energy will be equal to half mi into ri omega I whole square, right, which can be written as half mi ri square omega I squared, right? So we have an expression for what will be the kinetic energy of a particle when expressed in linear sense. But we already know one more thing, one simple thing we already know. What is that? What is this mr square? What is this mr square? We already know that mr square is nothing but moment of inertia of that particular particle, right? Reluctance of that particular spin, mass times radius square. It is nothing but moment of inertia. So we have that particular equation here, mi ri square. The only difference is that this is for an entire system while this is just for one particle. So how do we fix that? So we can fix that by taking the summation of all the particles from 1 to I. Or we can just take the integral, both are fine, but I'm going to take the summation since you're much more comfortable with the summation symbols. So I can say that Ke rotational will be equal to half summation over I is equal to 1 to n into mi ri square and let's say omega square. So if I take the summation over mi ri square, then I'll get mr square. That is the net moment of inertia of this entire particle, right? If I'm only taking for mi and ri, I can say that, okay, this particular particle will have moment of inertia mi ri square. But if I'm taking for an entire system, I have to sum up all the individual masses and all the individual radiuses so that I get the net moment of inertia. So instead of doing that, I inserted an operator which will do that for me, and then I'll get the output as half m r square omega square. But again, I do know that mr square is nothing but moment of inertia I. So since mr square is nothing but moment of inertia I, so I can write this mr square as half I omega square, which is equal to the kinetic energy of a rotating body. So the rotating kinetic energy of a body will be given by the equation half I omega square. It's very simple. The only thing you have to do is that consider a disk which is rotating at a speed of omega or angular velocity of omega. Then consider one random particle which is named as mass particle which is named as mi or mn, however you want, which is situated at ri distance from the axis. Then I can say that, okay, if I say it in terms of linear mechanics, I can say that it is having a velocity, linear velocity vi, which is, if I let go of this particular particle here, it will fly off tangentially, right? And it will fly off with the velocity. That particular velocity is indicated by vi only. So that is why it is indicated as vi. Then we start from there, and then we introduce a relation between velocity and angular velocity. Then again, we insert that and simplify that equation. We get the output as I omega square. And that is the expression for kinetic energy of a rotating particle. Okay, it's very simple, very easy. Okay, now what is center of mass? You might have heard center of attraction. What is center of mass? Okay, center of mass, if you have any heavy body, let's say you have some body like this. Okay, there is a point on this particular body or system where its entire mass seems to be concentrated in that particular point. For example, if I take this particular pen and let's say, okay, this is a pen like this. Okay, there is a point on this particular particle or this particular system where its entire mass appears to be concentrated. We assume like that. We assume like, okay, there is a point on this particular system where the entire mass of that particular system is going to be concentrated on that particular point. We assume that because we need to define what is translational motion, rotational motion and all that. So in order for that mathematics to happen, we assume that, okay, there is a point here so that it obeys certain laws. Okay, so we assume what is center of mass means. We assume that the entire mass of a particular body appears to be concentrated at a particular point. That point is known as center of mass. You might also hear this term, that is center of gravity. Center of gravity and center of mass, the only difference is that, center of mass is the point where the entire mass appears to be concentrated. Center of gravity just means that it is the entire weight that is being concentrated. Again, weight and mass, you know what is the difference? One is just m and one is mg, that is gravitational pull is experienced. So we can say that center of mass or a center of gravity is just the point where the object can be properly balanced. It can be known as a balancing point. For example, if I take this, it is an uneven object, right? Almost similar but uneven. If I want to balance it, even if I keep my hand at the exact very center, it won't balance. It will tip over. But if I adjust my grip or balancing point, then I can balance this pen. It is not exactly at the middle, but there appears to be a point where I can balance the entire mass of this particular object. So, because that point, the entire mass of this particular particle appears to be concentrated in a single point. So that is also known as balancing point. Much more easier or clearer definition would be regarding center of gravity, but again, this also works for center of mass. That is, the entire mass of a system appears to be concentrated in a particular point. That particular point is known as center of mass, or simply COM, center of mass. Now, simply we do this in order to define translational motion. That is, if I pick up the stick and if I throw this, then this end will be going like this, right? If I throw the stick, it will be going like this. It will be rotating like this. If I take a stick and throw it, if I throw it, first it will rotate like this, then it will rotate like this. If I focus on the end, it will be going in a spiral pattern. But we cannot actually predict what is the exact nature of motion. We cannot apply the equations of motion we already studied. We cannot apply any of those equations if we consider the edges like that. But if we consider center of mass, for the same object, let's say this is that particular center, then however I throw it, it just so happens that the center of mass is not changing. The center of mass is actually following a parabolic path. Even though the ends are rotating, the center of mass is still following the flight pattern we predicted in the previous chapters. That is a parabola. So a clearer example would be if we want to calculate the trajectory or apply the equations of motion for a grenade being thrown, then we can actually use center of mass to apply that particular equation. Because again, if I throw a grenade, it's both ends. Let's say this is the grenade. Doesn't look like a grenade, but let's assume that, okay, this is a grenade. This is a grenade and this is the pin. So if I throw this particular grenade like this, then this entire grenade will spin. At this particular point, it may come even upside down and it will be like this. So this particular point, or both of these extreme ends, is actually going on a spin. It is changing its position. So I cannot predict, I cannot say that, okay, I can apply the parabolic motion. I cannot apply the normal equations of motion we studied. But that is only because I'm considering the extreme ends. But if I assume that, okay, there is a point where the entire mass is concentrated and that is this particular point, then however it spins, there is no problem, because again, the center of mass is not rotating or changing its position rapidly. It is still following all the equations or all the necessary conditions for parabolic path, or how an object will behave when it is being thrown. A projectile equation can be applied onto this if we are considering center of mass. So that is why we consider center of mass and all these equations. So again, if I throw this, even though the ends are spinning around, the center is not changing. It is still following a parabolic path. So we can apply all the equations of motion. We can make some slight modifications, but we can still apply all the equations of motion. The object is still following a parabolic path, and all these conditions are still valid. So center of mass is an important concept if you're studying structural things and rotational motion and all that. So center of mass or center of gravity is considered to be a balancing point where the entire mass or weight of an object appears to be concentrated. It may be in the center, it may not be in the center. Because if I consider a baseball bat, let's say I'm considering a baseball bat which is like this. I know it's an unusual baseball bat, but let's say if it is like this, then obviously there is a clear weight distribution difference. Here it may be 1 kilogram. Here it might be 10 kilograms. Who knows? So there is not actually a midpoint. The center of mass may not actually be in a midpoint region. If this is the perfect center, the center of mass might not lie in the extreme center. It lies according to the mass distribution, because since the mass is more towards this side, I can only balance it maybe here. This might be the balancing point, which means the center of mass may be situated here. This might be the center of mass. Again, there is no compulsion that for an object, the center of mass should be in the center. The center of mass is the point in which all the mass appears to be concentrated. It is not the point in the center. That is the main difference. It might be where the mass is more, it might lean towards where the mass is less. Depends on the structure, depends on the mass distribution. That is why when you have a cycle, some people can actually lift the cycle, entire cycle, just using two fingers like this, just by grabbing the middle part. But if you try that with the one of the ends, it is very difficult because it will try to rotate. There are other factors influencing that also, but again, the point is that we can actually balance it if we apply or if we pass an axis through the center of mass. That is the clear example I can give you. But for a symmetrical object, if I take a symmetrical object, let's say I am taking a perfectly symmetrical cylinder, then I can say that, okay, since this is a perfectly symmetrical cylinder and the mass distribution is also very evenly spread out throughout this particular cylinder, the center of mass will be lying exactly in the center, right? But if I add 2 kilograms here, then what happens? The center of mass will shift slightly towards this side or this side. If I want to balance this, obviously I have to balance it a little towards this side, right? Depending on the mass distribution, I have to adjust my balance. So the center of mass is not a fixed point. Depending on the mass distribution, it actually varies. So that is some things you have to remember about center of mass. In fact, we'll do one thing. We'll solve and figure out what happens if we have a two-particle system and what will be the center of mass. What will be the expression for center of mass for that particular system. So we are going to find out what is the expression for center of mass of two-particle system. This is a perfectly simplified example. That is, if there is only two mass particle which is separated by a distance we don't know, so what will be the center of mass of that particular particle? What will be the equation for center of mass of that particular particle? So again, since we don't know anything about those particles, I am going to take that particular two-particle system in a plane. Let's say an XY plane. So again, this is going to be the y-axis and this is going to be the x-axis. So again, it's very simple. There is two particles which is separated by a distance. Let's say this is particle M1 and this is particle M2. And it is going to be, let's say this is the origin. So we can say that the position vector that is indicating the positions of M1 and M2 is indicated by R1, that is vector R1 and vector R2. So again, what will be the center of mass of this particular particle? So I don't know that if M1 is more heavy or M2 is more heavy. I don't know about anything. So I can say that, okay, I'm assuming that it has to be somewhere in between these two particles, right? Center of mass cannot be somewhere here, right? Because center of mass is going to be somewhere here in between these two particles. That much I know. So I'm going to take some random point, let's say this particular point, and assume that, okay, that is going to be the center of mass of that particular particle. Let's say I'm going to name it as MCOM, that is center of mass. Okay, so then I'll say that, okay, if I draw a line from the origin to that particular point, then the position vector RCOM, which means the position vector that is indicating center of mass will be drawn like this. So again, R2 is the position vector that indicates M2's position, and R1 is the position vector which indicates mass particle M1's position. We are only discussing about a two-particle system. Only two particles kept at a distance, and we are finding an expression for the position vector of the center of mass. Okay, so again, I know that, okay, RCOM is nothing but the position vector of the center of mass. So this much is only the figure. Now we are going to apply some small mathematics, and then we'll get an expression for center of mass of two particle system. So generally I can say that the position vector of the center of mass, vector RCOM, which means center of mass, can be written as, by summing up the individual position vectors and mass plus individual position vectors and mass. So that is, you can say that this will be equal to M1 R1 plus M2 R2 divided by M1 plus M2. So this is an expression in order to find the position vector of center of mass. That is, if two particles, let's assume that two particles are given in vector notations. That is, let's say the position vector of particle M1, which is having a mass of 2 kilogram. That is, if I'm saying that, okay, randomly I'm saying that, okay, 2 kilograms is placed here, another 2 kilograms is placed here, okay, and the position vectors indicating R1 and R2 is given by the equation. Let's say R1 is equal to 7i plus 2j plus 3k, like that, some other form is given, and R2 is also given, and they are asking you to find out, okay, find the position vector of center of mass, find an expression for the position vector of center of mass. In those type of situations, you can apply this particular equation. Okay, now sir, what if this is not the case and they have given the center of masses from the origin, that is only in the x-axis, that is the particular mass is kept like this and like this, 2 kilograms is kept like this, then what will happen? It's much more simpler now. Now we don't have to take the position vectors individually. We don't have to take x comma y. We can only take x because it is only expressed in x terms. So I can say that then the position vector R becomes position vector x only, because only in the x direction we are measuring. Then we can say that x center of mass, where x is the direction in the x coordinate, x center of mass will be equal to m1 x1 plus m2 x2 divided by m1 plus m2. There you go. Sir, what about if it is only in the y-axis? That is, if the two particles are situated like this, only in the y-axis, then again you only have to take y-axis. Y center of mass will be equal to m1 y1 plus m2 y2 divided by m1 plus m2. There you go. Simple. If it is given somewhere in the plane, you can use this particular equation. If it is given somewhere along the x-axis, then you can give this particular expression. And if it is given somewhere along the y-axis, you can give this particular expression. That is all. So you don't have to worry about how you can find this. Only problems will mainly be asked about this particular equation. You only need to know how to multiply vectors. If you know that, you can find the answer towards these two questions. And vector multiplication we have already learned in the previous chapters, so it's easy. Now again, one more possible question they can ask you is that, show that the entire object or the entire spinning object or rotating object moves as if the center of mass is moving along a straight parabolic line. That is, for example, the case when I told you earlier, if I spin something or if I throw something, even though the thing is actually spinning, the center of mass is not actually spinning, right? It is moving as if the entire mass is moving along that particular path. So if that kind of question is being asked, you can use a small derivation to show them. So the only thing you have to do is that consider a system which is consisting of n number of particles. Let's say you're considering a stick or a grenade or something where you're trying to throw that. So even though the thing is spinning, the center of mass is not going to change. The entire object is moving as if the entire mass is concentrated in the center of mass. Right, even though it is spinning like this, it is moving like the entire mass is concentrated at the very center. So that is what we are trying to prove here. So simple, we are going to consider a system, let's say a grenade. We are going to take a grenade and assume that, okay, it is made up of n number of particles. That is, if the grenade explodes, there will be n number of particles, right? So before that also, it should be n number of particles. So M1, M2, M3, etc. up to Mn number of particles are there, which means it is a system consisting of n number of particles, which is having n number of mass particles, which is also having position vectors indicated by R1, R2, R3, etc. up to Rn. That is, in the earlier case, we only considered two mass particles which had position vectors R1 and R2. Now we are considering n number of position vectors. If there is a grenade and if I place it, that is, if there is a grenade and if I place it here, let's say this is the grenade. If I place it here, then I can say that, okay, these will be the position vectors of the n number of mass particles, that is R1, R2, R3, etc. in space or in the xy plane. So I'm considering that n number of particles which is having masses m1 to mn and which is having position vectors r1 to rn. Then I can simply say that this n number of particles will have a total mass, that is, the total mass of this particular particle, total mass m, will be equal to summation over I to n mi, right? If I take the entire summation over this m1, m2, m3, that is m1 plus, m2 plus, m3 plus, m4 plus up to mn, I'll get the total mass of this particular system, which is I am naming it as capital M. Similarly, if I take the entire position vectors also and add it up together, then I can also say a similar thing, which will be equal to summation over Ri. So similarly, if I take the position vectors of all these quantities, let's say position vectors is indicated by capital R. So this entire mass is represented by capital M. Just like that, the entire position vectors, let it be represented by capital R. So I can say that vector R will be equal to, is it summation of all the R's, R1 plus R2 plus R3? No, right, we just saw that for a two system particles, that is R1 and R2, the net result or the general R is given by the equation R is equal to M1 R1 plus M2 R2 divided by M1 plus M2. How many masses are there? Multiplied with each individual position vectors, add them together, divided by the net masses which is present. So again, here we will also use the same trick, that is, how many masses are there? For example, it is going to be M1 R1 plus M2 R2 plus etc. up to Mn Rn divided by M1 plus M2 plus M3 plus etc. up to Mn. If I do this, I will get the net or general position vector of this particular quantity or this particular system. So instead of doing all that, I can simply say that, okay, since there are n number of particles or I amount of particles, I can simply say that this will be equal to summation over mi ri, okay, divided by, again mi, no, we know that the total mass mi is actually equal to capital M. So we can say that this will be equal to summation over MI/RI from 1 to n divided by capital M. That will give you the position vector or general position vector of a system like this. Now again, we can also express this in only the x-axis. If I'm only throwing the grenade in one direction, then I can say that, okay, it is one-dimensional motion. The grenade is moving only in the x-axis. Then I can arrive at an expression only in x-axis. If I'm only throwing it vertically upwards, then only in the y-axis. I can have multiple expressions because again, position vector R just means that it is x comma y comma z, right? It is all of these expressed individually. That is in the x-axis what direction, in the y-axis what direction, in the z-axis what direction. So again, instead of writing like this, I can always write it such as, okay, x is equal to, position vector x is equal to summation over mx rx. Position vector x is equal to summation over mi ri divided, not ri, but actually xi. So r is the general position vector. So here we can say that it is going to be mi xi divided by capital M. Again, if it is in the y-axis, I can say summation over mi yi divided by capital M. Similarly, in the z-axis also. So we can have multiple representations depending on if it is only in the x-axis, if it is in the y-axis, or in the general sense we can say that position vector r is equal to summation over mi/ri divided by m. So generally we can say that position vector is equal to summation over mi/ri divided by m. So that is one more way of expressing it, either in individual terms like this or in general terms like this. Both are possible. Now the derivation is not done. If any object is moving, we have to have an expression for its momentum. So we do know the expression for momentum, which is P is equal to, vector P is equal to mv, or in this particular case, I amount of particles or capital M, or simply mi particles are moving with a velocity v. But we just found out that the entire particle is going to move like this. And this r is nothing but indicating the position vector of center of mass. Okay, this expression means that, okay, this is the position vector of center of mass, which means that the entire body is going to move like the mass is concentrated in one particular position. That is, this particle, if I throw it, it is going to move as if the entire mass is concentrated in one particular point. So since due to that particular fact, I can say that the velocity of this particular system will be actually equal to the velocity of the center of mass of that particular system. So I can say that the expression for momentum will be equal to MIV center of mass. Or simply, I can say that, okay, let's say this Mi is the summation of all the masses present. Then I can simply say that, okay, summation over Mi, that is summation over Mi was already found to be capital M. So I can say that this will be equal to mv_com, or simply mass times velocity of the center of mass. Even though the entire mass is moving, the velocity is assuming that, retake. Even though the system is moving, we are assuming that, okay, its entire mass is concentrated in the center. It is moving like that because the velocity expression is for the center of mass. So that is why we assume that, okay, when I throw something, when I throw a system, it is moving as if the entire mass is concentrated at the center of mass. Okay, at a particular point which is known as center of mass. Again, this is not over yet. We can also apply Newton's second law here and find out. So we can apply Newton's second law here also and find out what is the expression for force also. That is, Newton's second law states that dp by dt is actually equal to, F, force applied, right? So instead of P, I'm going to substitute this particular equation. Then I can say that, okay, dmv_com by dt is actually equal to F, or simply keeping the m outside, since it's a constant, I can say that, okay, m dv_com divided by dt is equal to F. Now, again, we can express this one more term, that is, if I take the second derivative of velocity, if I take the second derivative of position vectors, I can actually give you velocity. This velocity is nothing but rate of change of position or displacement, right? So if I can write this particular equation as m d by dt of r, right? R is nothing but the position vector, or simply the position which is changing. So I can write this also. So how we write this double derivative is that we can write it as m d square r divided by dt square will be equal to f. Again, this is one more expression which you can use for finding center of mass. Again, you only need up to this particular point. I only gave you some general information on how we can apply that to the second law and actually derive an expression in terms of force and position vectors. So we can actually have one more expression like this. But again, for you, only this much is enough. It is very simple. It just means that what the equation states is that, okay, the entire mass of the object appears to be concentrated in one point when it is moving. So when it is undergoing rotational motion or all that, it appears that it follows a parabolic path only because the center, we can apply only certain equations because there is existence of center of mass. So center of mass actually helps us to explain translational motion. So what type of equations am I talking about? The very same equations we already learned about. That is S is equal to ut plus half at square, or V is equal to u plus at, or again V square is equal to u square plus 2as. If we convert them into their rotational sense, we can actually apply them to all the equations when we throw objects, where the object is actually rotating, because again, the body appears to be moving like the entire mass is concentrated in one single point. That is why even though we throw objects, it again follows a parabolic path. So again, we can just say that, okay, the rotational analogus of all these terms. S is displacement, which means it is theta. And we'll complete one equation at a time. So S is displacement, which is indicated by theta. So theta will be equal to ut. U is initial velocity. So I can say that angular velocity I, initial angular velocity times time plus half at square. A is nothing but acceleration. So here it is going to be alpha, which is angular acceleration squared. Again, in the next term, it is going to be omega f, because it is final velocity is equal to initial velocity plus angular acceleration times time. And in the final case, it is going to be omega f square, which is equal to omega I squared plus 2 into alpha times theta. So these are the analogous terms of the equations of motion which we already learned. This you can do on your own, and I have explained it in detail in the class, but still I thought you should know about this. And the concept of center of mass, center of gravity, all has been explained in the class. It's just a refreshing thing I just did right now. So I hope you'll all remember what center of mass is, how you can actually predict the patterns of things which is rotating, which is moving, like the entire mass is concentrated in one particular point. All these you know, but still I just wanted to refresh your memories because I know all of you are really smart. So I'll see you all in the next class with a new chapter. Until then, thank you.